So our second talk is given by Stefaan Vaes, rigidity for 2-1 factors. So please.
Okay, thank you very much. So I hope everyone can see and hear me and see the slides also in California. Maybe somebody can confirm this because I don't see what you see.
Yeah, we're fine. We hear you perfectly.
Okay, great. Thank you very much. Of course, I would have loved to be with you present in California, but due to the current circumstances, this was still a bit complicated from Europe. So it's a great pleasure for me to give this talk at IWOTA. And indeed, I will talk about 2-1 factors and rigidity for 2-1 factors. And in a minute, I will give you some basic definitions and basic background information, because I guess that not everybody is familiar with the topic. But before doing that, let me give you the basic philosophy of what I want to tell you. So what I want to tell you is that there are all kinds of mathematical structures, could be groups or actions of groups, on all kinds of other structures or groupoids or many other things, and they give rise to 2-1 factors, which are specific types of von Neumann algebras, and I will come to that in a minute. And the philosophy of the talk is that there are two very distinct paradigms. The first one that we coined the many-to-one paradigm is that in surprising and often highly inexplicit ways, very distinct initial data, very distinct groups or distinct group actions may nevertheless in a surprising way give rise to isomorphic 2-1 factors. And then on the other side of the spectrum, I will talk quite a bit on the so-called rigidity paradigm or the 1-to-1 paradigm, where exactly the opposite happens. So different types of groups and group actions and so on may be so that the arrow that sends the group to its von Neumann algebra is 1-to-1. Now, of course, we have to specify then in which sense this is 1-to-1. And this can be, of course, plainly up to isomorphism of von Neumann algebras. It could be up to so-called stable isomorphism, because as I will explain, 2-1 factors have the property that you can take T by T matrices over them. So of course, we all know what are n by n matrices over an algebra, but we can do that with any positive real, as I will show you. And then there are all kinds of variants of this isomorphism notion as well that will come up later. So let me now first go back to the basics and the basic definitions. So this goes back to the fundamental work of Murray and von Neumann in the 1940s. So what is a von Neumann algebra? It's an algebra of operators on a Hilbert space, closed under taking the adjoint, so the star, and closed in the weak topology. And equivalently, by the famous bicommutant theorem, such an algebra can be characterized as those algebras that are equal to their bicommutant. So the commutant of M consists of all operators that commute with everything in M, and M is equal to its bicommutant if and only if M is such a von Neumann algebra. Now, these von Neumann algebras, they come in different flavors, and a first obvious reduction, a kind of simplicity assumption, is to look at factors, so those that have a trivial center. So that's the appropriate simplicity assumption in this theory. And then Murray and von Neumann classified them in different types, type 1 being the trivial case. The type 1 factors are those that are exactly B of H, all bounded operators on some Hilbert space. And then the 2-1 factors are those that admit a tracial state. And these are really the basic von Neumann algebras to study, because in a way that I cannot explain you today, any von Neumann algebra is in a way built up of the obvious type 1 and then the much more fundamental type 2-1 factors. There is, thanks to this tracial state, a kind of continuous dimension, because of course, the trace on B of H we are familiar with, and the trace of a projection gives you exactly the dimension of the range. here we will work with normalized traces, and remarkably, the trace of projections in a 2-1 factor ranges over the entire interval 0, 1. So therefore, this notion of this wording of continuous dimension. And 2-1 factors, as we will see today, and as I will try to convey today, it's an extremely rich structure. So many mathematical structures can be reflected into 2-1 factors and then give rise to interesting questions. Now, thanks to this continuous dimension, I can come back to the previous slide and go back to these T by T matrices, because n by n matrices over a 2-1 factor gives you a new 2-1 factor. But then we can take in n by n matrices a projection which has precisely trace T, where T is any positive real, and we can take that corner of these n by n matrices, and in that way define m to the power t, which we will see appear a few times. And this is really well defined. I mean, essentially up to isomorphism, it doesn't depend on the choice of this idempotent. Okay. So how do 2-1 factors arise, for instance, from groups? So when you take a countable group, and I will come to that condition in a minute, when you take any countable group, a discrete group, you have its left regular unitary representation. So you represent G on the Hilbert space little L2 of G by left translation operators. So on the canonical orthonormal basis, this looks like this. And then the first operation you could do is to take the linear span of these unitary operators. And what you define in that way is the group algebra C of G. And taking its weak closure, of course, you get a von Neumann algebra, and that is called the group von Neumann algebra. That construction is also going back to Murray and von Neumann. This one always has such a nice trace, and it is precisely a factor when G is sufficiently non-commutative. And the condition is that G should have infinite conjugacy classes. So any non-trivial element in the group should have an infinite conjugacy class. Secondly, a bit more complicated, is the construction of still Murray and von Neumann of group measure space 2-1 factors. So here the initial data is not just a group, but it's a group acting on a measure space. So the group acts by transformations of a measure space, and we assume that the measure is a probability measure, that the action is measure preserving. So that will be usually abbreviated as PMP, probability measure preserving. And then in order to ensure that we get a factor and a good theory, the assumptions are that the action is sufficiently non-trivial, and we will right away assume that it is free. So stabilizers are trivial, say almost everywhere, and that it's ergodic. So G invariant sets, they have either measure 1 or measure 0. And in that case, you can build a 2-1 factor. And this 2-1 factor is usually denoted like this. It's a crossed product construction. It resembles a bit semi-direct products for groups. And this von Neumann algebra, A cross G, it contains two things. It contains, on the one hand, L infinity of X as an abelian subalgebra, but it also contains the group von Neumann algebra L of G. And the two, they interact as they interact with in group theory. Namely, if I take a function and if I conjugate it with a unitary UG from my group von Neumann algebra, then this normalizes this function algebra and it reflects the action of the group on the space in this way. And then you can see what the algebraic structure is. There is a canonical trace, and together with that canonical trace, you have a completion, and you get this basic object. Okay, so these are the basic players. So let me now go to the first and one of the two most famous many-to-one results, all the way going back to Murray and von Neumann still. Such a 2-1 factor is said to be hyperfinite if you can somehow build it up from finite dimensional algebras. So when there exists an increasing sequence of finite dimensional subalgebras, star subalgebras, with the union being weakly dense in M. And the canonical construction of such a hyperfinite 2-1 factor is given by taking an infinite tensor product where you at each step take tensor product with 2 by 2 matrices. And at each stage, of course, there is a unique tracial state. So there is also a unique tracial state on the algebraic direct limit you can complete. And what you get is the Murray-von Neumann hyperfinite to one factor. Now, the first surprising many-to-one result is that any hyperfinite to one factor is isomorphic to this specific one, R. So here, for instance, whether we have taken 2 by 2 matrices, or we could vary the matrices at each stage, or whatever other variant of the construction, all hyperfinite to one factors are isomorphic. Moreover, this unique hyperfinite to one factor is kind of really basic, because any to one factor contains many copies of the hyperfinite to one factor. So this is really like the basic object of the theory. Then Murray and von Neumann, they went on and they speculate that they didn't use the word to one factor. They more, well, in a more twisted way, they speak of a factor in the case to one. And they speculate that the possibility might exist that not only R embeds into any to one factor, but that conversely, any to one factor can also be found as a subalgebra of R. And that therefore, the possibility exists that any to one factor would be isomorphic to a subalgebra of any other to one factor. Now that is of course wrong, as we know nowadays, but at that point, that was one of their speculations. And this is the good occasion to introduce the notation that will come in the second half of the talk, namely to study this question: when does a given to one factor can be realized as a subalgebra of another given to one factor? And maybe we can allow for so-called amplifications. We put the S of stable if there exists an amplification of T, so T by T matrices over M, such that N can be embedded into MT unitally. So this is the first many-to-one result. The more famous one is the one of Alain Kohn, and that has to do with amenability. So let me first explain you the notion of amenability, actually also a notion of John von Neumann in his explication and his interest in the Banach-Tarski paradox. So a countable group G is said to be an amenable group if you can find the translation invariant mean on G. Now, this is a kind of counterintuitive thing because it is a finitely additive probability on all subsets of the group that is translation invariant. Typically, this is a kind of non-constructive thing that you only show to exist. Yeah. Now, this notion can be transferred to von Neumann algebras. There is also a notion of amenability for von Neumann algebras. And a von Neumann algebra is called amenable if there is the appropriate equivalent of such an invariant mean. And this is expressed as a non-normal, so not weakly continuous, conditional expectation of B of H back onto M. Why am I saying this? Because amenability turns out to be something really intrinsic and important for von Neumann algebras, because a group to one factor L of G is amenable if and only if the underlying group G is amenable. And secondly, it can be proven that that amenability passes to subalgebras. So if M is an amenable to one factor, and if N can be embedded even into N by N matrices over M, then N is forced to be amenable. So therefore, we can already answer this speculation of Murray and von Neumann, because it's wrong in the sense that if lambda is a non-amenable group and gamma is an amenable group, for instance, lambda is a free group and gamma is your favorite amenable group, say finite permutations of a countable set, then there is no possibility to embed even stably L of lambda into L of gamma. Now, what has this to do with many-to-one paradigms? Well, one of the most famous theorems in the theory, due to Alain Kohn, and say half of the work for which he got the Fields Medal, is that all amenable to one factors are isomorphic. So there are loads and loads of amenable groups with infinite conjugacy classes, very distinct groups with no relations between them. Nevertheless, their group von Neumann algebras, they turn to be all isomorphic to this unique hyperfinite to one factor. Another consequence, because of amenability passing to subalgebras, whenever a to one factor can be embedded into R, it must actually be isomorphic to R. So this amenability is a very striking notion. Yeah? So that's one extreme. All amenable structures basically give rise to one and the same hyperfinite to one factor. Then there is the other side of the spectrum, where there is a lot of rigidity. And one of the very early results of this, and developed by Sorin Popa in his so-called deformation rigidity theory, one of the most striking results to state in this context without too much technicalities is by looking at group measure space to one factors that come from Bernoulli actions. So what is the Bernoulli action? This is a nice example of a probability measure preserving action. So take any group G, take your favorite probability space x0. It could be just 2 points with weight 1/2, 1/2, or any other weights you may want to assign to the 2 points. So you take your favorite probability space, you take a group, and then you take an infinite product of your probability space indexed by the group G, and you let the group G act by translating the coordinates. So of course, this infinite product, you may view this as functions from G to x0, and then this is just a translation of the function, of course. So that's a nice ergodic probability measure preserving and essentially free action. So almost every point has a trivial stabilizer. So this gives rise to a to one factor by the group measure space construction. Whenever you take for G an amenable group, you always get up to isomorphism the hyperfinite to one factor. Although you can typically not do this explicitly. Even when G is just Z or Z to the N, it's not at all so easy to explicitly see that this Bernoulli cross product is isomorphic with the hyperfinite to one factor. Okay, so that's one thing. That's the previous result. Now, when G is very far from being amenable, we get exactly the opposite phenomenon. So let me explain this in steps. So for instance, if G has Kazhdan's property T, and let's make things very concrete, take for G the group SLNZ, where N is at least 3, so N by N matrices with entries in Z and determinant 1. Then actually, this to one factor, this Bernoulli cross product, entirely remembers the group and its action. So what does that mean more precisely? It means that if you would realize this same to one factor in any other way as a cross product, then the two groups must be isomorphic and their two actions must be the same, must be equally isomorphic. So this is the most extreme form of rigidity, where the entire initial constituents, they can be recovered from this ambient to one factor. So therefore, this is coined a W star super-rigidity theorem, where W star refers to W star algebra. I mean, this is a synonym for von Neumann algebra because of the weak star closed nature of von Neumann algebras. So this result, as I just stated this, for groups like SLNZ is due to Adrian Ioana. I think that must be somewhere in the middle of this range of years. But of course, there was an initial version with more asymmetric assumptions in the fundamental work of Sorin Popa. And then, since then, it has been developed for many other types of groups, in particular for direct product groups. So if you take any non-amenable direct product, so assuming that one of the groups is non-amenable, say a free group, and the other one is infinite, any infinite group, then you have this rigidity phenomenon as well. And that's then from a joint work in 2010 from Sorin, Popa, Adrian Ioana, and myself. Okay, so this is one type of extreme rigidity where the entire initial construction can be recovered from the ambient to one factor. Okay, let me now turn to group von Neumann algebras. There are many very interesting open problems. So I guess many of you have heard of the free group factor problem. So this is really one of the 2 or 3 most tantalizing open problems on two-one factors. We do not know whether the free groups with n generators give rise to isomorphic or non-isomorphic two-one factors. Of course, for n at least 2, yeah? For n is 1, you get an abelian algebra. So thanks to free probability theory, so thanks to the work of Dan Voiculescu and then later Florin Radulescu, we do know that there is a sharp dichotomy. So either they are all isomorphic or they are all non-isomorphic, and this even includes the case n is infinity. Now, quite remarkably, this is related to the question whether the group von Neumann algebra of the free group with infinitely many generators is singly generated, which sounds like an absurd question, because of course your answer would be obviously no. But still this is open. So the question is, can you give in the group von Neumann algebra of the free group with infinitely many generators a single element such that the star algebra generated by that single element is weakly dense in L of F infinity. Even worse, it is open whether there is even any two-one factor that is not singly generated. Of course, we have to put in small print here the obvious condition that we work in the separable world. Yeah, of course. So two-one factors acting on a separable Hilbert space. So of course, if you could disprove that L of F infinity is singly generated, then you would disprove that L of F infinity is finitely generated. And then, of course, you would have solved the free group factor problem, because then it cannot be isomorphic to L of F2, yeah? Or L of Fn for any finite n. So one other reason why I like to state this open problem is because it does show how intricate these questions on isomorphism of two-one factors are, yeah? Because even for such simple groups, this is widely open. Another class for which it's widely open is for lattices in Lie groups. So contrary to the free group factor case, there is a conjecture at this point. So if you take such a lattice, and let's make things very concrete, take, for instance, SLNZ again, and for the even ends, we divide by the center. So to be sure that, so the center with 2 elements, yeah, plus or minus the identity matrix. So you get these groups PSLNZ. And here there is a rigidity conjecture due to Kohn saying that if the group two-one factor of PSLNZ would be isomorphic to any L of gamma, then this should force gamma to be simply isomorphic to PSLNZ. So Kohn predicts this kind of superrigidity again for lattices in these higher rank simple Lie groups. Again, this is really wide open. The only, say, poor man's result we know is that there can be at most countably many non-isomorphic groups that give the same two-one factor, which really sounds as an empty result almost, but it's not empty, because if you take the free group with 2 generators, you can prove that there are uncountably many non-isomorphic groups that give the same two-one factor. Yeah? So there is a little bit more of rigidity known already. Okay, this kind of superrigidity phenomenon for group von Neumann algebras has been established, though, for other classes of groups. And the first family of groups for which it was established, so the first such superrigidity theorem for group two-one factors, was proven by now a while ago by Adrian Ioana, Sorin, Popa, and myself. And we did construct groups G such that their group two-one factor entirely remembers the group G. So whenever L of G is isomorphic to a group two-one factor L of lambda, the groups must be the same. And I will not tell you how these groups look like. I mean, they are a bit cooked up. They are of the form of a so-called generalized read product construction. So they are of a semi-direct product nature. They contain an abelian normal subgroup, which is the group of two elements, direct product I times, where I is a countable set, an infinite countable set. And then gamma is acting on I and then shifts the indices. And in that way, you get a semi-direct product group. The reason I'm saying that is because later on, with a former student of mine, Mihai Berbec, we could do the same with much more natural examples. So actually for many, many so-called left-right read product groups, where you take gamma a group, countable, you take the group with two elements to the power gamma, and then you can both shift to the left and shift to the right. This gives you automorphisms of this abelian core. And then the semi-direct product will very often be such a W star super rigid group. And this happens, for instance, if gamma is the free group, or if gamma is any free product group. Okay, let me turn to another type of applications of these, this deformation rigidity theory of Sorin Popa. And that has to do with one of the most interesting invariants of Murray and Van Neumann, although they gave a strange name to it because they called it the fundamental group, which of course already at that time had a clear meaning in algebraic topology. The fundamental group of a 2-1 factor in their terminology, it's always a subgroup of the positive reals. And one way to say what it is the group of positive reals T, such that M is isomorphic to T by T matrices over M. Another way to say the same is that it's the group, it's a subgroup of R plus consisting of all ratios of traces of projections, where P and Q are projections such that these reduced to 1 factors, these corners, are abstractly isomorphic as 2-1 factors. So Murray and Van Neumann, they were very happy with this invariant. And then at the same time, they write in their paper a sentence saying that they are frustrated that they could not turn it into a useful one because the only computation they could make would give the entire positive real line. So the only thing they could prove is that the fundamental group of the their hyperfinite 2-1 factor is the entire positive real line. And of course, they had no means at all to disprove that the fundamental group would be R plus just for any 2-1 factor. So that was only disproved much, much later by Alain Cohn, who proved that if G is a property T group, think again of P as ln Z with n at least 3, then its fundamental group must be a countable subgroup of R plus. Even though also Alain Cohn had no tools at all to determine the fundamental group, but he could prove that it must be countable. Then Radulescu could prove that for the free group with infinitely many generators, it is always, it is the positive real line. And it follows from this that solving the free group factor problem is equivalent to determining the fundamental group, because there are only two options. Either L of Fn with n finite has trivial fundamental group, and then all these free group factors are non-isomorphic, or they all have fundamental group R plus, and in that case, they are all isomorphic. So that's the situation. The problem whether there could be actually 2-1 factors with a trivial fundamental group stayed open until Sorin Popa came up with deformation rigidity theory. And then he could produce this very concrete example, namely you take the group SL2Z that acts on the two torus in the obvious way. Yeah? So you realize the two torus as R2 mod Z2, and SL2Z acts on R2 in the linear way, and then it preserves Z2, so you can take the quotient. And this semi-direct product, this cross-product construction, has a trivial fundamental group. Then he went on by making variants of the construction and could prove that any countable subgroup of R plus can be realized as the fundamental group of a 2-1 factor. And then with quite different constructions, we could actually, Sorin Popa and myself, realize many uncountable subgroups as fundamental groups of 2-1 factors, but acting on separable Hilbert spaces. I mean, we do stay in a very concrete setting. Now, this raises a very interesting descriptive set theory problem, namely, it's wide open to characterize which subgroups of R plus can arise as fundamental groups of 2-1 factors that act on some separable Hilbert space. So on the one hand, we know that there is a restriction because all these subgroups of R plus, they must be Borel sets, which is of course a very weak restriction. They must be so-called polishable. There exists some Polish topology on these groups such that they become a Polish group. But still, that's a very wide world of subgroups of R plus. The ones that we can realize, they are still much tamer. They are all countable unions of compact sets. So they are not so extremely wild in the set theoretic sense. And there is a big gap still between what is realizable and the restrictions that are known to hold. Okay, let me now turn to a few more recent results that have to do with this possibility of which 2-1 factor can be embedded in which other 2-1 factor. And before explaining you the situation here on the slide, I already mentioned very early on in the talk that something non-amenable cannot be embedded into something amenable. Now, there are many variants of this basic idea, and one of it due to Alain Kohn and von Johns, showing that if lambda is a group with property T, say SL3Z, while gamma has a flexibility property that was introduced by Uffe Heuerup, the so-called Heuerup approximation property, think of a free group, then actually it's impossible to embed L of lambda even into an amplification of L of gamma. So here is a nice and qualitative non-embeddability result. For instance, there is no room in L of F infinity and even into its amplifications to hold the group factor of SL3Z. All this follows from the possibility to intrinsically define property T and the Heuerup property for 2-1 factors, but I will not go into that. Yet another variant of that has to do with the Cowling Heuerup constant. It's a little bit more with a numerical thing. So if you take this simple Lie group, SP1n, and you take gamma n, a lattice into SP1n, then you can prove that there is no room to embed L of gamma n into L of gamma m if n is larger than m. What's the reason behind? There is a notion called Cowling-Heuerup constant for 2-1 factors. You show that it decreases under embeddings, and Cowling and Heuerup manage to determine the constant for this kind of 2-1 factors that are arising from lattices in Lie groups. Why am I stating these results? To show you that these are qualitative results. I mean, it's based on properties. I mean, of course, here it's a numerical invariant, but still the basic idea here is that more rigid objects cannot be embedded into less rigid objects. Now, the kind of non-embeddability results that I want to show you now, they are of a different nature. So let me first still add a few open questions and related things. So here is a nice one. Let me focus on the one of Ozawa. To show another way to say how many 2-1 factors there are is that there is no universal one. So there is no separable 2-1 factor that is large enough to accommodate all 2-1 factors as a subfactor. So there is no 2-1 factor in which any other one can be embedded, staying in the separable world. Another nice thing is that on property T groups, this arrow that sends a group to the von Neumann algebra is countable to 1. So if on property T level, there are only countably many non-isomorphic groups that give the same 2-1 factor. Anyway, here again, open problems on embeddability. If n is larger than m, it's conjectured that there is no room for PSLNZ into PSLMZ on the 2-1 factor level, although we have really no clue how to prove this. Here is a nice one that has a flavor of group theory. So for those who are familiar with amenability for groups, they may know the von Neumann-Day problem. So the typical non-amenable group is the free group with 2 generators. And then von Neumann and Day, they asked whether all non-amenable groups contain F2. So a group that contains F2 must be non-amenable. But then later on, it was disproved, and this von Neumann-Day problem, and there were constructed these very weird non-amenable groups that nevertheless do not contain F2. Well, on the 2-1 factor level, this problem is open. And it could very well be true that any non-amenable 2-1 factor does contain L of F2. I believe that this is true, actually. So that the behavior is really different from the group theoretic level. And then conversely, which 2-1 factors embed into L of F2? And here there is a general belief that the only ones that can embed into L of F2 are themselves essentially free group factors or the hyperfinite 2-1 factor. Anyway, let's turn to the more recent results on embeddability. And they have to do with, again, this kind of left-right Bernoulli shifts. So what's the freedom that we take? We take a base algebra with a trace, and it could be very well an abelian algebra. I will even take a 2-dimensional algebra in a minute. So you take any base algebra that is amenable and has a trace. Then you can take an infinite tensor product of it indexed by a group gamma, and we will just take the free group. You can shift the tensor product by left translation. You can shift it by right translation and build this left-right cross product. And the theorem that we proved earlier this year with Sorin Popa is that in this specific case, embeddability is extremely rigid because you can abstractly embed such an algebra in another one of the same nature, even stably, even only if you can do it for canonical reasons, because already on the level of the initial data, there is a trace preserving embedding. Okay, this may sound a bit as abstract nonsense, but let me illustrate this with the easiest case. You can take as a base algebra a 2-dimensional algebra. And then, of course, a trace on a 2-dimensional algebra is just determined by the weight you give to the atom. So you have a parameter A, which can be any number between 0 and 1. And then the trace looks like this. And what you get is a family of 2-1 factors. And that was open to construct such a thing. A family of 2-1 factors indexed by this number A. And you prove that they cannot be embedded one into the other. So you have this continuous family of 2-1 factors, and none of them embed into any of the other ones, even after taking amplifications. And then you can start playing games. As a probability space, you could just, instead of taking 2 points, what you do is you take the interval from 0 to A with the Lebesgue measure, which has weight A, measure A, and then you add the remaining measure as 1 minus A as an atom at the point 1. You perform the same construction, and what you get is 2-1 factors indexed by this number A between 0 and 1. And what you get is that you can embed MA into MB, even only if A is smaller or equal B. So now we get like a chain, a continuous chain of 2-1 factors, and they are canonically embedded when A is smaller or equal B. And when A is larger than B, you prove that it's impossible to embed, even in any abstract way. So here we had mutually non-embeddable 2-1 factors. Here you have a chain. And then you can vary this in many ways. And for instance, you can also build 2-1 factors that can be embedded all in the other, but that nevertheless are not isomorphic, not even isomorphic after taking amplifications, and so on. So the the options are endless. Let me show an application on the fundamental group, or rather its one-sided variant due to Adrian-Johanna. So we have seen that the fundamental group of Murray and von Neumann was the group of positive reals such that M is isomorphic to T by T matrices. Its one-sided variant is the set of positive T's for which M can be embedded in an abstract way into T by T matrices over M. This has the structure of a semigroup. So it first of all always contains the natural numbers because you can embed M diagonally into M by M matrices over M. But now you can also compose embeddings, so it's stable under multiplication. You can take the direct sum of two embeddings, so it's stable under addition. And then once you have a single element in F between 0 and 1, since you can also take infinite direct sums and you can take compositions, once there is a single element between 0 and 1, you must have the entire positive real line. Adrian-Johanna could not turn this into a computable invariant in many cases because all known computations led to one of the two extremes, the smallest possible or the largest possible one-sided fundamental group. Now, with the very rigid structures that Sorina and I introduced, we can show that any countable semigroup actually does arise, and in a very concrete way. Of course, if you're not into 2-1 factors, you will not feel familiar with infinite free products and so on, but you can take as a base message that if F is countable and satisfies the semigroup properties, there is a machine that builds you a 2-1 factor for which exactly this F is the one-sided fundamental group. Here is a very wild construction. So the very wild construction is a functor that it's a very canonical thing, really a functor, that assigns to any infinite group gamma another group H gamma with infinite conjugacy classes, and embeddability is exactly reflected as it was for groups. So it's a functor such that the group factor L of H lambda embeds abstractly in an amplification of L of H gamma, even only if you can do it on the level of the group. So even only if you can do it canonically. I think that, yeah, there is some space, and the space here on the slide is to show you that it's extremely concrete, the functor. But still, I won't bother you with it. I mean, the slides are recorded, so you can pause it if you wish. It's an extremely concrete construction of this group H lambda in terms of lambda, and you prove that there exists an embedding of L of H lambda into L of H gamma, even only if lambda embeds as a subgroup of gamma. That can be exploited to prove all kind of wild families of 2-1 factors. So I had this concrete construction that I showed you earlier, where you have this chain of 2-1 factors, where MT can be abstractly embedded into MR, even only if T is smaller or equal than R. Well, actually, you can now exploit the previous result and build, I will come to the conditions in a minute, what you can build is for any partially ordered set, you simply build in a concrete way a family of 2-1 factors Mi, and you prove that Mi can be abstractly embedded into Mj, even only if I is smaller or equal j in this partially ordered set. So the world of 2-1 factors is as rich as it can be, because any partially ordered set can be realized by families of 2-1 factors that can be embedded or not according to the partial order. Now, of course, this any is exaggerated because we want to stay with 2-1 factors on a separable Hilbert space. So of course, you need on your partial ordered set a kind of separability assumption. And again, it's probably not worthwhile to go into details here. You may invent yourself a good notion of separability for a partially ordered set. And it's exactly for these separable partial orders that you can realize them as families, partially ordered families of separable two-one factors. Okay, let me turn to the two final results, which are a bit easier to present. And the one has to do with symmetries of two-one factors. So two-one factors typically have a lot of automorphisms. And they also have the so-called inner automorphisms, because if you take a unitary in M, the conjugacy with that unitary U defines you the automorphism that sends X to UX U star. So you have inner automorphisms. They form a normal subgroup of all automorphisms. And the quotient is called the outer automorphism group of the two-one factor. Now, the nicest case is the one of so-called full two-one factors, namely when the inner automorphism group is a closed subgroup of the outer automorphism group, of the full automorphism group. In that case, the quotient group is again a nice Polish topological group. And the question is, can you determine this? Can you determine this group of outer automorphisms and then of all automorphisms of a given two-one factor? So that is typically extremely difficult. I mean, for instance, the outer automorphism group of the hyperfinite two-one factor, it's extremely huge. I mean, it's this kind of set theoretic object that you cannot describe. For instance, it contains any locally compact group. Any locally compact group can be embedded into the outer automorphism group of the hyperfinite two-one factor. Now, for some of these very rigid two-one factors that we construct, you can actually determine all outer automorphisms. And then you can start wondering, what are the possible symmetry groups of two-one factors? And many Polish groups are known to arise by now as outer automorphism groups of two-one factors. For instance, all closed subgroups of permutations of n. Any permutations of n. So this is a huge family. It's like all groups that can act on countable structures. Also, all locally compact, totally disconnected groups can arise. All compact groups can arise. Of course, all countable groups can arise. Even unitary groups of Neumann algebras can arise as outer automorphism groups, which sounds like a bit of a weird statement. But again, there is this difficult open problem to intrinsically characterize which Polish groups, which topological groups can arise as symmetries of full two-one factors. And this is, of course, as a problem, strictly harder than saying which fundamental groups, which subgroups of the positive real line can arise as fundamental group, but at least as interesting. Yeah? That is the main thing I wanted to tell you. So thank you very much.
Now it's unmuted.
So thank you very much for your talk. Any question? Any comment? Any question? So if not, let's thank the speaker again.
Thank you very much.